will start broadcasting. Okay, that's started. You can go ahead.
Go ahead now.
Yes.
Okay. Good evening. My name is Michael Powell, and I am going to discuss technical details and scalability of NoSQL. With regards to NoSQL, the discussion items, we're going to discuss what is NoSQL, why it is and how it is, how does it work. We're also going to talk about the NoSQL databases, types of NoSQL databases, NoSQL terms, differentiated products. We're also going to look at a comparison between Amazon's DynamoDB and Apache HBase. We're also going to look at different data models, Amazon's DynamoDB data types, throughput HBase data types, and indexing. So when we look at NoSQL, we must first understand what it is. NoSQL is a non-relational database. It's a semi-structured databases. It's also schemaless and uses a variety of data models. So with regards to NoSQL, databases are non-relational, where it's optimized for potential scalability with performance, and it's based off of also schemaless data models. NoSQL databases are also widely recognized and deployed due to their what's considered their ease of use and being able to have low latency as well as resilience. When we look at asking why we use it and how does it actually work, well, the uses for data modeling are within the uses for data management. From the research that I've conducted thus far, it can house large volumes of data. We've already talked about the low latency and the flexibility of the differentiation within data models that can potentially become more complex within relational databases as opposed to non-relational databases like NoSQL. When you start looking at aspects of big data being able to carve and work with large amounts of data, the added value is for mobile and web applications to be accessed and potentially be displayed globally. The offer is also with the greater scale and offers high responsiveness as well as the being able to have simpler data structures as opposed to potentially more complex within more structured environments such as relational databases, where there's a potential with relational databases for as more schemas that you potentially add to relational databases becomes more complex. And the added value is also with horizontal scaling within NoSQL. And looking at the databases and NoSQL databases, we also have to look at the data models. There's no enforcement whatsoever with regards to the actual schema. And there's a partition key, which is for retrieving values. There are ACID properties that are also flexible within the data model. And we also talked about this earlier, where the scale, it can scale horizontally. With the performance, in specific models that I've seen conducted over the research, and this is just the hardware piece, the technical pieces, where the determinant is also what determines performance is the hardware cluster size, which can also determine which can also either promote or diminish network latency. And the performance is also with application calling. And looking at the scale, you have distributed clusters that can also promote added value within increased throughput. So within NoSQL databases as well, we also have differentiated APIs that make it easy for storage and retrieval. And once again, we talked about the partition keys, and we're going to talk about this in a little minute, in just a minute here, as we migrate and started talking about specific tools that are used to access data. The tools for managing clusters and scaling, and this is pretty much like the primary interface that users would use to access the data within NoSQL. And looking at the differentiated types of NoSQL databases, there is columnar, document, graph, and in-memory value stores, key value stores. Columnar databases are optimized for reading and writing columns of data as opposed to rows of data. Column-oriented storage for database tables is an important factor in analytical query performance. And when we look at the document databases, those are designed pretty much to store semi-structured data as documents, typically in JSON or XML format, unlike traditional, more structured models dealing with relational databases. The schema for each NoSQL document can also vary, giving you more flexibility in the organization and the ability to actually store application data and potentially reducing storage required for optional values. You also have graph databases which store vertices and direct links called edges. Graph databases can be built on both SQL and non-SQL databases. And the in-memory value stores are NoSQL databases optimized for read-heavy application workloads such as social networking, gaming, media sharing, and question and answer portals. Now, in understanding NoSQL, there's one thing that I found that was a little interesting within my research, and it dealt with the actual terminology. Within this graph right here, and this is a graph from the Amazon portal, AWS portal, dealing with white papers, where I noticed the differentiation from NoSQL product to NoSQL product, and it's actually within the terminology. As you can see, there's a differentiation within the actual terminology from product to product, from MongoDB all the way through Couchbase. So that's one thing that threw up, going from product to product, there is a learning curve where it's with regards to the actual terminology. This screen here shows the actual database products, where we've already talked about the different database types from key value store, columnar, or document store. And these are the actual differentiated products for NoSQL. And the two that we are going to discuss today moving forward is Amazon's Dynamo and HBase. When you look at Amazon's Dynamo here, DynamoDB, the hosted solution, what it offers is a fully managed NoSQL database, where if it's hosted, there is no administrative overhead. It's virtually unlimited throughput and scale. It's more elastic as well as flexible, meaning, hey, you could probably just, if it's a subscription-based model, you could just pay for what you use as opposed to just buying and having potential excess. And it easily integrates within other products within Amazon's lineup regarding NoSQL. Apache HBase has the Hadoop database, which its added value benefits are efficient storage, sparse of data, storage for high frequency counters, high write throughput and update rates. Also has support for multiple Hadoop jobs. And the Apache HBase data store allows data to be used by one or more Hadoop jobs on a single cluster or across multiple Hadoop clusters. Now, within, there was a specific white paper that I downloaded from the AWS website that dealt with a comparison for Amazon DynamoDB and Apache HBase. And the actual features are differentiated and talk over the different operating systems hosts where the Amazon's Dynamo is hosted, whereas Apache is differentiated amongst Linux, Unix, and Windows as far as a different operating system. But I also took into consideration too with this and understanding the actual APIs and the tools, the methods for accessing specific data on the back end. As you could see, there are the different APIs and other methods of access through RESTful HTTP API .NET. And it also shows the differentiated uh, supported programming languages between the two non-SQL databases. And once again, too, the features are differentiated regarding the throughput. Uh, Hold on, let me go back here. Let me also show within there are server-side scripts also involved, and the partitions are both shared. Okay, when you look at also the data model, there's a differentiation between the row size, the primary keys and the foreign keys. And just to reiterate on the slide prior, the different database types and the actual terminology, as well as the actual products. The actual terminology is differentiated from product to product, just to reiterate. The transactions are also differentiated as well. How Amazon DB and Apache are used. Now, within the white paper that I read concerning their specific comparison, it gave specific examples of use cases and why these two databases, NoSQL databases, are added value. Now, in high volume special events, these could be, and just as an example, these can be such popular events such as Super Bowls, Olympics, the World Cups, or seasonal events where there is a potential for a short duration run that has variable workloads and the potential to consume large amounts of resources at one time. With the actual use of the Amazon DynamoDB, lets you dial up capacity when you need it and dial it back down to handle, once again, variable workloads. Another example is with social media applications or what's considered community-based applications such as online gaming, photo sharing, location-aware applications that have unpredictable usage patterns and the potential to go, and I'm pretty sure I'm using this term widely, going viral at any potential time. There's also batch-oriented processing for large data sets, such as long data, weather types of data, product catalogs, and large amounts of data that are considered historical that you want to maintain for potential historical trends. Reporting as well is the process and report on high volume transactional data, such as daily stock market trades. With this, the white paper actually recommends Apache HBase as being the better product over DynamoDB. Now, with realistic analytics, this pretty much is the payload or the message size within the event. And with the example of such tweets or e-commerce, relatively small in comparison with application logs. So if you want to ingest a streaming event data in real time for sentimental analysis, ad serving, trends analysis, uh, the recommendation is with Amazon DB. That'll let you dial up throughput throughout capacity when you need it, and then dial it back down when you are actually complete. The differentiated data models, one common ground, and I really shouldn't use that word differentiated because both models have a common denominator, and it's with their key value stores where the added value is delivery of performance, the promotion of low latency, and the promotion of high throughput. And once again, I have to reiterate this because the terminology is differentiated from DynamoDB and HBase as well. And looking at the different the data types, DynamoDB data types, you can look within the table, and this here shows the different types, the description types, and the different JSON examples of how it's broken down within the different types here. Regarding the throughput model, the throughput model is differentiated and by item size, expected read and write request rates, consistency, local secondary indexes, and global secondary indexes. And when we talk about throughput, and let's see, within indexes are indexed by a primary key for fast retrieval with the Amazon as well as Apache NoSQL products. The secondary indexes are extended with the basic indexing functionality and provide an alternative query path in addition to queries against the primary key. So when we look at the when we look at the Amazon DB, it supports two kinds of secondary indexes. And it supports local secondary index and global secondary index. The local secondary index is an index that has the same hash key as the table, but different range key. When you look at the global secondary index, it's also an index with the hash and range key that can be different from those of the table. H-base data types, row, column, part of the column family, you have the timestamp as well as the value. And looking at indexing, and I apologize, here when we look at indexing and regarding this table here, the local secondary index organizes data by the index range key rather than by the range key for the source table. And this is actually two tables put together. Every local secondary index contains a hash and range attributes from its parent table. A local secondary index can copy or project some of all of the attributes from the source table and provide an alternate query path for efficiently accessing data. Within this example table here, it introduces the local secondary index. This index contains the same hash key. The actual person ID is considered a source table and also defines the top score date as its range key. The range key value from the source table automatically projects or is projected or copied into the index, but is not part of the index key. And this is just a continuation of that table. And the differences, and as I said, with the actual differences between DynamoDB and HBase is how it's hosted. It's also differentiated by the actual terminology. But when you consider big data, the added value overall is with being able to place data in large data sets and be able to carve and be able to cultivate data to make requests where speed and accuracy are not any type of issues. These are just some of the technical aspects that I've come across concerning my research. And in looking at big data, the first thing I would have to look at is, and utilizing NoSQL, is I'd have to look at the terminology and I'd have to conduct the usability from, let's say, product to product, from database type to database type, where, as a matter of fact, a lot of it too is upfront is going to be determined by those business owners and the types of businesses they run and the types of technologies that they need to leverage for big data as far as what they're trying to do. So with that being said, this pretty much concludes my presentation with regards to being able to scale NoSQL.
If you compare the two databases, I mean, not just compare the two databases, but in general, talking about scalability in NoSQL, how would you identify the main methodology for the scalability of NoSQL? I'm asking because there are like the classical examples of how SQL databases can be scaled, and there are vertical and horizontal scalability, and I believe there will be one presentation today about this. But what are the techniques for the scalability of NoSQL databases?
What are the techniques for the scalability of NoSQL databases?
Right.
The techniques.
Maybe you have found some examples, or say the Amazon case. This is the hosted environment, and that's pretty hidden from the end user how the scalability works for the end user. As long as there is demand, we just assume that the database will get scaled. But for example, the Apache option, the HBase, they are not hosted. So you have to actually control the way how your database will scale up if there is the growing demand for the data throughput. So how would you control this?
I don't know how I would control it, but I can tell you that I ran across a couple of white papers on the Amazon website, but they didn't deal a lot with the technical aspects, dealt more with total cost of ownership. And a lot of and within this one white paper that I've read, the lowest total cost of ownership was with the use of the DynamoDB over everything else, because of the costs associated with the software, the hardware, the also scalability, the more so scalability, and being able to virtually increase resources from a cloud environment versus from an on-premise solution. But like I said, I was trying to do more technical, but I ran across something that just dealt with the actual total cost of ownership.
And in your opinion, the cost of the ownership is more appropriate in Amazon solution just because you pay as much as you use instead of paying for the facility to run pretty much constantly. Is this the case?
I think the case with the Amazon was the uptime, the ease of use, the sustainability, and the ability to have more so scalability during peak times, and just to scale back during times when they're not so busy. But the actual there was an actual statistic that was presented that dealt with stops and slowness and how much it actually costs the organization every second that something is not a specific transaction doesn't occur. If a specific transaction doesn't occur, it was X amount of dollars per second per minute that it cost the organization. So the added value is with the hosted services and being able to add value with specific redundancy from region to region as it related to overlap and failover services in case one region went down.
All right. Thanks. Any other questions?
No, I don't have.
All right. So we move on to the next presenter. Do you have any request to be the next presenter?
I mean, I can go if you want.
Okay, go ahead.
Hey guys, good evening. This is Hemant Saxena.
Could you share your screen?
Yes, I'm gonna go do that. I was not sure if I put mine, just take away his presentation, so I just waited for it. I'm just
run the slideshow.
Can you see my screen?
I can see the screen, but it's still not the slideshow. Now I don't see the screen.
Now you don't see the screen?
No, not now.
Yeah, sooner I did on that mode. When
you want to choose the share entire screen like you did before.
Yeah, let me do that actually. Yeah, that's a good option. Okay, and is it better now?
Yeah, that's good. Can you advance the slide to see if? Yeah, that's good.
Thank you. So this is Hemant Saxena, folks, and I did my research around distributed computing in big data, and try to see that how it get applied, what is the need around in big data. And then I actually went specifically to see one of its specialized framework implementation in big data, and how does it satisfy the need of it. So basically, in this presentation, what I'm going to do is, because I'm more specifically interested in researching about the distributing components and the system involved in big data and all. So I want to we'll go quickly through what is basically what we go with the characteristics of a distributed system, what is the motivation when we want to go distributed, and the challenges we go, and then we will see what we understand by big data, and where the big data computing, distributed computing fits in the big picture. And then we'll go with to see what is the big data motivation for its distribution architecture, and what kind of solutions we have when big data need to apply its solution, whether we go traditional enterprise solution or we go some specialized framework. And then we'll see how Apache Hadoop answer those big data need for distributed computing and distributed system. And then, like I said, that I did my research on how those different component in Apache add to those distributed computing, and which all the different components get into play. So that's what I'm gonna cover in this presentation. So do you have any questions or any thoughts about what we're going to discuss right now?
Well, just go ahead.
Perfect. Okay, so like I would be keep switching between the word called distributed system and distributed computing, at least in the grand schema of what we're discussing today. It's basically my whole focus is to see when this computing is happening, whether it's the computing is happening at a distributed level, and which will definitely involve a distributed system. So when we go to distributed system, generally the idea is that it is the combination of either of distributed hardware, distributed control, and the distributed data. So generally distributed hardware is we share the same physical memory or distributed physically distributed memory. And once we come on the control, in the distribution control, we have either master slaves, which is a fixed scenario, or dynamic in the sense that if a master dies, then somebody takes over and become the master. That become dynamic. And then multi control points. In this multi control point, in the sense that you have one sector of resource which is managing that, or is a heterogeneous system of system which are managing that. And then how the distributed data is handled in those scenario, whether we copy it, the whole data to the processor. And this processor is not the computer processor. Processor is the node which is supposed to work on that data. So whether we copy to the processor, or let it remain with the source and then just processor works on it, or we just divide the data among the processors to make it a smaller chunk so that it could be transferred there. So this is what I'm gonna basically fundamentally take my presentation towards, and then we'll apply all these things of distributed system and see how it works in big system architecture. So now various architectures which are supported in distributed systems are like, we know it's clusters, grid, P2P, or we see that in storage systems, so on. So generally we use clusters when there are a group of computers that appears to be a single supercomputer, computer. And I don't know whether that we support in big data or not, but mostly what we do support in big data systems and all is grid type of architectures. Basically, there's a coordinated and sharing and aggregation of distributed, autonomous, and heterogeneous resources. So that will be more interest for us when we look big data architectures for a distribution system. Then we also know there are P2P networks, which is completely decentralized. We in our daily life we have used torrent or something like that, or file sharing, instant messaging, that kind of architecture we know about. And generally in distributed systems, the communication protocol among the system involves RPC calls, direct TCP/IP, or HTTP calls. Now the characteristics which we see in a distributed computing, and which we will going forward see in our when we apply any specialized hardware to solve the big data need, is that it need to be heterogeneity, in the sense that multiple autonomous component, maybe of same type, maybe of different type in terms of memory, operating system, RAM, and bandwidth, could work together. And then definitely the concurrency, so that when we are working on the common goal of resolving an analytics, take an example, then they can work in concurrent. We need to have multiple point of control, so that if a failure happen, somebody can switch and take the control. And plus it's more in the performance sense, that the controls are divided among different entities there. And then multiple point of failures, so that if one node gets down or one machine gets down, that doesn't become failure of the whole goal. High availability is the number one characteristic which is look in any distributed computing, which means that if I gave a worker a node of work, and it's for some reason it becomes flaky, then there's like any multiple point of control system detects that, take the work away, shut down that flaky node and give it to the other one. So basically, any processing unit which we want high availability, it's still consistent in processing, which is the next point which is coming on that availability of that working on that unit of task was high. It was just not lost. And that particular point actually brings the second last important point, which is the consistency. Like if we have broken down a piece of work in, let's say, 1,000 unit of work, and when we finish, they finish in the order we want and nothing is lost there. And the scalability, which is the distributed system should be able to scale, like Michael was talking about, dial in and dial up, and it should be able to do it based on the load it's addressing to. Now, what actually, so I talked about the characteristics that what we are looking at, but what actually motivates to go on distributed computing? So basically, there are 4 or 5 important things which drives any platform or system to go on distributed computing. One is the volume and velocity of data or even processing. Volume is like quantity of the data, and velocity is the speed at which we are generating the data. So I'll take this examples of each of this when I'll discuss it in terms of big data, that how that works. And then the other motivation factor is the performance versus the cost. So working on the complex and volume of data in distributed configuration definitely outperform adding parallel resources. The scaling and maintaining the parallel resources is definitely become a challenge when things get bigger and bigger. Another thing is like geographical resource sharing. I mean, like if you're like, for example, like if you're doing banking transaction in multiple geographical area, you can easily share your hardware with the hardware in that particular country or region. So that's another reason for motivation. And high availability and fault tolerance, like I described before, that high availability is become the number one point for any distributed computing to behave on. Then scalability is the motivation. The heterogeneous processors can be added without affecting performance if running on this. It just goes with the condition that if heterogeneous processors are added, and if they are on the same middleware algorithm, basically same communication language, they won't affect each other performance. And then the last point is the enhanced reliability, basically because the reliability could be achieved by possibility of replication resource and their execution. So these are the important motivations when you go to the distributed computing. And distributed computing has its own challenges, and we'll see how those get addressed when we discuss about one specialization, a specialized framework implementation for big data. We'll see that how all these challenges get addressed there. So distributed computing need to deal with the following challenges in the real world. So first is definitely the complexity of heterogeneous data. Like data can come from cell phones, data can come from social events, data come from IoTs, data come from semi-structured, unstructured data. It could be mails and those kind of things. So the distributed, when the computing happens, that need to deal with all kind of data, and that's where we will have those discussion of different storages which address those needs. Then complexity of distributed state. So now within a single computer, all the system resources are correctly serialized because they exist as at one point. They places all the operation on a single time, so we get the total ordering in that case. And at any moment, say, we can get to know the state of every resource in the system, but that is not available in terms of when the components are distributed. So ordering is a challenge in there, and knowing the state of the resource and the data it worked on is a big challenge too. Then the complexity is there in the management. So service may be configured with different options. So every node, every resources, and every basically component has to be configured similarly, or maybe depending upon the system they're supporting to. Then different functions which has to be assigned, like I was talking about, that multiple controls, like everybody, different components can have their own set of roles defined in the distributed system. So we to assign that and manage that. And then definitely the versioning of the function. So I mean, the solution will keep growing up. We will have different functionality to manage those things are the one of the biggest challenges there. And the last one, I mean, this is also a very important one, that once the higher loads gets up into a system, it start uncovering more and more weaknesses of the system. So higher load often uncover weaknesses that has never been problem in the lighter load. More node means more messages, which may result in increased overhead and longer delay. So you have to figure it out that if something is lagging or delaying in the system, then it could be one of the reason that because of the load, things are getting slower down. So that's an important factor in distributing computing. So this what I just talked about is what do we see in distributed computing. Now I'm going to talk about big data. Let me know if you have any questions from the past section, and I can continue with the big data then.
Go ahead.
Okay. So what is a big data? Basically, how do we say what kind of data is big? What size of data is considered to be big and will be termed as big data? So big data as a terminology boils down to the amount of data which is just beyond technology capability to store, manage, and process efficiently. So it's an enormous amount of data which cannot be handled via traditional way of computing. So the other reason why it is that way, because big data is the data whose scales, whose diversity and complexity requires new architecture, techniques, algorithm, and analytics to manage it. I mean, it scales like we can take the example of Google search, we can take the example of Facebook. The data just scales exponentially every day, and the diversity of data which we are dealing these days is enormous too. Different type of data from videos like YouTube, the kind of data it's handling, then the photographs, and then IoT producing the data, and the complexity in the sense that when we do want to do some analytics on those data, it become really complex, and then we need a new architecture and techniques around it. So big data, the data itself has the characteristics of high volume, high velocity, and high variety information asset that demands cost effective and innovative form of information processing for decision making and process automation. Basically, when we talk about big data, generally we are talking about it's the volume and the velocity of it has been produced, and how we can use that data to do for our decision making, or like process automation, or for analytical. Generally, the big data whole thing is more look from the point of view for analytics. I mean, when we collect all the data, we want to do analysis on it so that we can make a good decision on it. Big data also refer to the technologies and initiative that involve data that is too diverse, fast changing, or massive for convention technology, skill, and infrastructure. So basically, in overall, the data size and the velocity is driving how we can compute on it and how we can make a decision out of it. So big data, it is a data computation that needs the power of many computer. Data could be in terabyte or petabytes, and it can use thousands of CPU in parallel or both. So it demands a cluster of computer for both storage and analytics. One of the few examples where the data is classified as big data are example of search maps, which raw disk can use 5 petabyte of data and can consist of 1500 nodes. I'll show more in detail in that, the detail of the nodes there, what it is actually mean by. But right now I just want to show the kind of data which generally categorize into the big data thing. And then there is a LHC colliders data where the colliding detectors tap on the events of 1 petabyte of data per second. Can you imagine amount of data it produces? And then the analysis on happen, how the particle accelerations things work. Then the same big data is generated for banking. For the fraud detection, they take whole set of data, behavioral data, and do the analysis on it. Doing traditional way of putting analysis on it will take I think years of traditional computing. Same goes with the stock transactions too. We also generate a lot of data when we do processing of astronomy data, when we sense all the satellites and spaceships up there. They produce tremendous amount of data which has to be real-time computed, and that's where again produce data of type big data basically. And Internet of Things, as we are aware that now we have sensors almost on everything, every devices, every electronic component which sends tons of state events, and that also produce huge amount of data. So this is, I've already kind of went through that big data. And when we talk about big data in any aspect, three V's get important there. So which is the volume of the data, which is the amount of quantity of data which is being created like every hour. The Walmart customer transaction provide the company with about 2.5 petabytes of data. I'm not sure whether this is talking, this is the quantity of per year or per month, but it's just talking about the quantity. And then we will come out the velocity. I mean, how fast we are generating those data. So Facebook users sends on average of 31.25 million messages and the views of 2.77 million videos every minute on every single day over the internet. And then the third part of the third V is the variety of data. So we get the variety of data as structured and semi-structured data, like sending emails or sharing pictures, audio clips, video clips. They're all terms as unstructured data. Any questions on here?
What about others depicted on the picture to the right?
Yeah. So, yeah. This is more. So these are more aspect of big data. Like we already did volume, velocity, and variety. Then the validity of data, the governance around it, then the variability of it, variability in the sense that the data source which is generating it, how it evolves, and how different type of data it produces in terms of size and characteristics. Then we also talk about the data venue, which system, which platform it has been generated from, and how it affects the data behavior. And then once you have all the data, it has to be translated into a vocabulary. some semantics so that it could be structured, it could be queried upon, it could be stored on the databases, like Michael was talking about those databases, edge bases, and Amazon one. There has to be a key pair value, and same concept, big data's implementations goes on to that. Once a vocabulary is set, the data is divided into key pair value before it process. And the vagueness is confusion over meaning of big data and tool use. Sometimes Facebook is a very big company, but even for mid-sized company, if they are producing a terabyte of data, it could be a big data for them too. Yes, so basically what it means to say that data doesn't only apply to big organizations, but could be used low level organization or mid level organization to apply the framework for, basically, to get the answer on. Okay, so this is one of these. I like this slide in the sense that it gives you the big data foot in the distributed environment. So if we have the data ecosystem, I don't know whether you can see my mouse where I'm pointing.
Yes, we can.
Yeah. So this is the area of big data, and you can see how different type of data are getting influxed to be processed, which finally get integrated to the data warehousing. Ultimate goal is to produce visualization data and analytics data, or some online business application. So basically, you can see the streaming events, maybe a perfect example like Super Bowl or something Michael was talking about. They're continuously streaming it. They're capturing the behavior out of it, integrating with the data warehouse, putting the visualization right in front of the commentator, and he can say that this is how he behaved the last year at the same moment, at the same point, how he tackled it, or now how weak he's become. So that real-time processing happening right here, which is then going into the warehouse for the visualization there. And it's also showing that how data warehouse takes from other legacy system to the data to process that. So yeah, this is one of the very good slide to at least give you the big picture on what is the space, big data space in the real world scenario.
What are those abbreviations? CRM, SCM, ERP?
I think it's content management, data management, and I don't know what CS for here.
I meant the ones that actually getting fed into the extract, transform, load into the data warehouse. CRM, SCM, ERP, legacy, these blocks. Yeah, over here.
Over here?
CRM, SCM, can you comment them? This one.
This one? I mean, I think like CRM is customer relation management, like Salesforce and all the data coming from there is good. I'm not sure with HCM. I think some content management system. I forgot. Yeah, and this is the ERP, the accounting and all those kind of things come from that. And then your legacy is the applications which you are using in-house, like airline system, booking engine, and some third-party data. So basically, in an organization, this is generally this setup goes. Like when I used to work for Cox, they all their ad capturing data come from these systems. Like they have the legacy system, they have customer relationship management coming from Siebel. So they all goes into there and make a meaningful sense with what all we are doing, computing from the Hadoop, from the big data side, basically.
Okay.
Yeah. Okay, and now I've already set up the mood for motivation of distributed architecture, but I'll just go ahead and reiterate why big data is more motivated for distributed architecture. So big data technology needs to achieve any type of analytics in fast and predicted way, and that's the main reason why it's more motivated for distributed architecture. It wants consistent reporting data, enabling for better human and machine level decision making. Consistency and high availability goes in hand, that need to be really there. And principle of distributed computing are the keys to big data technology. All the principles and the characteristics in combined we saw. Basically, it's also around the stipulated cost and the time practical analysis for consumption by human and machine. I mean, we can have all kind of data, but if it is cost of doing any computation or getting to any results is not time practical and not costly, is no use. So speed of computation is very important, and it applies to every area and every mechanism around it, which is the data storage, which we'll see the data access part of it, how we transfer the data, whether we do the transfer of data or we stay near to the data, and how effectively we can do the visualization and apply the predictive model around that distributing process in multiple low cost machine. I mean, if we don't want to go on a specialization machine just to process the data, so that kind of thing will drive the cost. So if we can use any kind of machine power which is available, that is what big data demands in distributed architecture. Now, looking at the big data and see how an organization apply these solutions towards it. There's a traditional enterprise approach framework which the organization can go with, or there are some specialized framework. In traditional, we all see that you can have a client server architecture, you can have multiple servers supported behind alias, and they, depending upon round robin fashion, try to address your computation need. Or we can have decentralized peer actor system, little better than client server, but it's still not very well managed, and state management is still a challenge there. And then we have hybrid of hierarchical or decentralized by message passaging. We have MPI cluster or grids, message passing interface clusters, but they still, all these traditional approach fails in many aspects of high availability, synchronability of the task which has been distributed among the grids, and the scalability. How do you scale? How do you determine when to scale? That all are missing in traditional enterprise approach. So that's where we look forward to a specialized framework. We categorize the framework on two things. One is the data intensive, and one is compute and data intensive, in the sense that it works on the data. Once it has been data has been how do I say that, is being sanitized to be used. So the data intensive, today our focus will be around Hadoop. This is where I made the learning around the components and how it works. So any questions on this computing solutions? Any questions here till the time before I move to the specialized framework of Hadoop?
Just go ahead.
Hope I'm not going too fast. I feel that I'm going too fast.
You're not, but you have to leave room for others.
Yeah, I think I don't know which slide I'm to. Yeah, I'll go fast a little better on this. So Hadoop, the main thing is that Hadoop is a software framework. It is not a hardware framework. So there's nothing hardware configuration is involved. It's all managed by a software that allow for distributed processing of larger data sets across the cluster of computers using only programming models. There's no hardware acceleration or something, or hardware anatomy is changed or anything is done. So whatever the resource is present, we use that in the programming model. It is designed to scale from single servers to thousands of machines, each offer with their own local computation and local storage. And when it comes to the local storage, we'll talk about it. The Apache Hadoop is a framework for storing as well as processing of big data. So basically, when the data is generated, it's just not a framework of processing it. It can store it too. So it's capable of storing and processing all form of data like structured, semi-structured, and unstructured data, and works on directly on stream of data too. So how does Hadoop address big data architecture need in terms of data storage? We know about Apache Edgebase, which is one of the component it used for storage. It gives you the computing power. It gives you the fault tolerance. If a node goes down, jobs are automatically redirected to the other node to make sure the distributed computing does not fail. This has been done by multiple copy of all the data which are stored automatically. Now it has the flexibility. You can store as much data as you want and decide later how to use it. It's a low cost because it doesn't force you to use any kind of commodity hardware, specialized hardware. It can work based on the commodity hardware which you have at home, offices or something. And scalability is scalability works beautiful in case of Hadoop architecture. It has a separate resource manager which works on it. I'm going to talk about that. And with the little and so before coming on the framework, this is what is Hadoop ecosystem. So this is where I'm saying that Hadoop core, not only there are distributed component, but all these distributed component also execute their function in distributed computing mechanism. So they're just not localized to one node. They span across the node to get their work done too. So basically, the base of Hadoop system, like we said, that we have a data storage. We have HDFS and Edgebase. Both are used for storing the data. Then data processing is another key, which is based on the MapReduce, and the Yarn, which is for the resource management. It basically manage how MapReduce on each machine will work on. Then how we take the data from different systems. These are the technology which are involved to pick the data from different resources, and how to work on like Hive SQL, how to create a job for MapReduce to work on it.
Okay. We no longer see your screen.
Give me a sec. I might have to rejoin actually. It says retry. Hey, can you hear me?
Yes, we can.
I'm sorry, I don't know what happened with Google. Even connecting initially gave me a lot of trouble to do that. So I'll just share the desktop again. You can see my screen?
Yes.
Okay, thank you. Thank you for your patience. And I'm sorry, I'm not keeping track of time. Actually, I should have done that. I'm more. I've crossed the limit.
Slightly, but go ahead and finish what you have to say.
Okay, so at least I'll go with the key component of Hadoop structure, which is the MapReduce and HDFS, and then other slides I'll just go through. So the way Hadoop works, there's a two views which I'm sharing on the screen. One is the data view, and one how the node view. Basically, all the scaling of the nodes happen on the Hadoop. So what is the concept of map and reduce is like if we are standing in a library and we have different rows and we have to count how many books are there, and we all five, let's suppose five of us goes down there, so we are mapping ourselves each other to count the books, and when we come back and give each other our count that this many books are there, that step is called reduce. So basically, if you say so basically what it does, that it takes all the work, split it into chunks, give it to the node to process, and once the result are there, like you can see here in the cow and dog example, when you get the counts here, it just reduce it to that cow has 2 counts, dog has 1 count, and that's the output it saves. So that is the main architecture of Hadoop map and reduce. And you can see that how input comes, which comes on the HDFS on the node view, gets split into multiple nodes, which they map and work on the data and finally get reduced to a meaningful output. Now, so Hadoop HDFS distributed file system architecture, what it does, that any data which is actually stored on it, it's split into larger blocks. It is designed for streaming reads and append writes, and not very much supported for random access. It's like you're just writing it and working on the data as it comes. So the way it maintain the high availability of the data is by replicating of 3 replica of each piece of data by default. Data can be encoded and archived in formats. HDFS is self-managing and self-healing in the sense that bring the computation as physically close to the data as possible for the best bandwidth instead of copying the data. That is one of the main feature of HDFS shelving concept, that it tried to avoid the cloning of the data. It tries to use the same node and the same rack and the same data center when working on the data. Auto replication is there if the data is lost, and it auto kills and restart of the task on another node if it is taking too long, or it finds it too flaky. So basically here is the two important concept of Hadoop, of high availability, how does do the nodes name servers and node servers are maintained. And here's it shows how those data are replicated among different namespace basically. This is the another important piece of Hadoop, which is the scheduling manager. This is called Yarn framework. It is separated out in Hadoop 2 to more manage the resources. So if this the resource manager is the one which do the negotiation of scaling up and down depending on how much workload is there. That's how the skills work on it. It has 3 components, which is resource manager, node manager, and application manager. Now, resource manager manage and allocate the cluster resources, manage the scheduling, and manage the application managers. Node manager is actually is the what generates the node and give the work to the containers here for job submissions. And this application manager actually manage the scheduling of the task of the execution based on the priority of the task which has been set up there. Yeah, this is one of the example which tells you how job is actually induced in Hadoop, and how different component, like we discussed, the MapReduce program, SDFS, and node manager comes into the picture. Then Hadoop has another important component which is called Zookeeper. It is a distributed coordinating service for distributed app. Basically, for high availability, it actually manages the coordination and notification among the different nodes which has been created for the work. It select the leader election, in the sense if masters dies, and then who will become the next master, and put the distributed locking in case of data consistency is required. So basically this is used for high availability system here. And now once the data is in there, this is how the people, query using pig, one of the scripting, you can ask for the data here. So one sample data here is like, you want to load the user with this name, filter by pretty much like an SQL query. Like you can do the users, you can put the filter, pages how many you want to load, joins you want to make, group by and sum by. So that's how the data could be learned from the SDFS store directories. Now, way to run Hadoop, you can run Hadoop like we mentioned before, which is a need that it can be any kind of heterogeneous system. You can run on Linux, OS, Windows, and Solaris. You just need a Java and access to those nodes, some XML configuration files to define the node. If you can use via Amazon Elastic MapReduce too. They have their GUI or command line cluster management utilities. They can support both streaming of data and with the Hive and Pig thing. You can grab the data and MapReduce code from these sources, like from S3 bucket, and put it in SDFS. And auto shutdown EC. So basically, feature of scaling of EMR could be done through EC2 instances. I think this is last ones. Yeah. So just to give you perspective, when now companies has implemented Hadoop in their distributed computing, what the size they have reached on. So Yahoo cluster has like 17 million files. This is talking about the cluster has 17 million file, 18 million blocks, 15 petabyte capacity of 400 plus nodes. These are the nodes which are actually involved in map and reduce process. The Facebook, we already know that how much data it produces. So the Hadoop system consists of these many million blocks of data, and the objects, which is a file and blocks, basically storage, videos, and pictures, and the chats, and having of 21 petabyte of capacity with number of client. These are not the client which using the Facebook, but these are the client who is managing the Hadoop cluster. Basically, same goes with eBay. The amount of data and client is enormous there too. So these are the three major companies which are having big implementation of Hadoop. Any questions or comment? I'm sorry, I just went too fast on the last slides, which actually needed more homework and discussion. I'm sorry, it just went over the time.
That was comprehensive.
Yeah, when I went into it, I just keep noticing everything, yeah, and jotting down those things.
Are you currently working with this Hadoop system, or you just decided to learn this for this presentation?
In my and my last company, we one of the project demanded it. I was part of it, but then I quickly moved out of it to do something else. So yeah, the experience is still very basic, but very impressive actually.
So you mentioned Facebook, eBay, and can you mention some other companies who use Hadoop for the storage solution?
Aeronautical companies, the Boeing use it a lot, and then FlightAware, which constitute every flight moving out in the space. And I mean, banking ones where they have to do the fraud detections. They work on Hadoop, or even making the offerings to the customer. They look on the behavior. Then I mean, yeah, plenty of company which are data and customer intensive uses this Hadoop now. I mean, they Hadoop and Sparks go hand in hand. I don't have the clear differentiation where people start moving to Spark, but I think Spark is a little more lightweight than Hadoop. And I see people when I was doing research on this, that people are tendency to move on Spark to a lot now these days.
I think if you just have two computers, you can set up the Spark environment, but for the Hadoop, you probably need more resources.
Probably, yeah. So right. I hope you enjoyed in my fast-paced delivering of this content.
That was good. Thank you.
So it's a megabyte. Thank you to you all. Thank you so much.
Mm-hmm. So anybody wants to be next?
I think
Janak? Okay.
Yeah. Okay.
Hello everyone. I'm Janak Ratsabagai, and my today's topic is distributed operating systems, modern alternative of RMI and RPC. Modern alternative to RMI and RPC. Okay. Some people are just saying RMI is just related to Java, and it is a lot to code. It is too much. It is tedious. But it is a good way to start. It is good way for the learning phase. And yeah, that's what I included. Drawbacks of Java and RPC, strictly Java, and then they say that it cannot guarantee that the client will always use the same thread in consecutive calls. Meaning we need to write a mechanism for identifying the client ourselves. There may be some other drawbacks too, but I included these two. Okay, there are a lot of alternatives till date. Some are old, some are new, and some of them are like JMS, EJB, RACE, JSON, Plan9 from Bell Labs. That I find out that impressive. It was old one, but I saw that was pretty appealing. It is Amoeba, CMDS, D-Unix, that is also from Bell Labs, and much more. We can use other web platforms too, Azure, Amazon Web Services, and all. Okay, now I am describing about JMS and REST. In one part, I'll describe REST with JSON, and let's start with JMS. Okay, the full form of JMS is Java Message Service, and it is an application program interface from Sun Microsystems that supports the formal communication known as messaging between computers in a network. The JMS provides a common interface to standard messaging protocols and also to special messaging services in support of Java programs. Sun advocates that the use of JMS for anyone developing Java application which can run from any operating system. Basically, it can be used for any operating systems. Okay, the messages in JMS are involved the exchange of crucial data between computers rather than between users, and contain information and service requests. Messaging is often used to coordinate programs in dissimilar systems or written in different programming languages. It means we can use various programming in various use with various programming languages. It's not like RMI or RPC that you have to use just Java. Using JMS interface, a programmer can invoke the messaging services of IBM's mQueries, Progress Software's Sonic MQ, and other popular messaging product vendors. Okay, now after this short introduction, I'll move towards the architecture of JMS. Okay, we can see that it has the four components. One is JMS provider, one is JMS clients, uh, another is messages, and another is administered objects. Okay, let's talk about the JMS provider. JMS provider is a messaging system that implements the JMS interfaces and provides administrative and control features. And implementation of Java EE platform includes a JMS provider. And talking about JMS clients are the programs or components written in Java programming language that produce and consume messages. Any Java EE application component can act as JMS client. Okay, and let's talk about the messages, which are the objects that communicate between JMS clients, administer objects, JMS. Okay, okay. Okay, now let's talk about the administered objects. Administered objects are pre-configured. They are always pre-configured JMS objects created by an administrator for the use of clients. Okay, the uh, JMS, the administered objects are they are already configured, and then they are uh, they are already made by the administrator, and then um, it is used by the clients. Okay, let's describe this figure now. We are seeing it over here. Um, the administrative tool allow us to bind the destinations and connection factories to the JNDI namespace. The JMS client can then use the resource injection. Okay, it injects the uh, resource, and then JMI client can use the injected resource and access the uh, administered object in the namespace. Okay, access the administered object in the namespace, and then establish a logical connection with JMS provider. Okay. Now let's move to the JMS queue load balancing model. There are two models actually. One is uh, topic, that is public and subscribe model. Another is queue, that is load balancing model. Let's discuss about queue load balancing model. It is also called point-to-point model. Messages are sent from one application to another application using a queue, means through the queue, and there can be more than one consumer listening to the queue, but only one of them will get the message. Only one of them will get the message in this queue load balancing model. And now let's discuss about the JMS topic, public and subscribe model. Um, Here in this model, we can see that message is sent to the multiple consumer through the topic. The topic is the here the topic is the link between the subscriber and publisher. The subscriber may or may not acknowledge the published message. Implementation like JMS acknowledge the message, the messaging providers, but not the sender of the message. Publication will be received by all subscribers. Yeah, these all three subscribers will means uh, will receive the message. Not like the previous one. Previous one all will acknowledge it, but every one of them will not get that. And uh, okay, if there are any new subscribers on the same topic, uh, they will not get the publication until uh, unless there is the publication is retained. Okay, now that's all about the architecture of JMS. Now let's discuss about the advantages uh, or features of the JMS. Okay, the first advantage is asynchronous communication. Asynchronous communication. Okay, in JMS, request initiator is not going to wait for the response, and it is uh, wait for the response, and it just send the message out, then close the connection. Okay, it just send the message and then suddenly close the connection. Uh, we don't need the backing service up at the time of the communication. We don't need the backing service. Okay, and JMS is loosely coupled. JMS has the ability to decouple related system. Instead of sharing the database, the systems will be communicating by the system boundaries. And the communication in JMS is reliable. Message once sent will be delivered to the customer or consumer without any loss of data. Also, message will be sent only once. And there is a lot of industry support. Uh, the Java API is really simple, and uh, load balancing and many more. I just highlighted the three points, uh, and okay. For another as another alternative, I have selected the REST, and I'm gonna introduce uh, it to you guys. Okay, the word REST was found by the uh, guy called Roy Fielding to describe an architecture of network system. RESTful systems view the HTTP endpoints that can be distributed across different services as resources that have an associated associated set of standardized verbs like get, put, post, delete that can be invoked to interact with the resource. RESTful APIs can be self-documenting and easily discoverable. Okay, now let's move to the REST architecture. It contains of the three parts. It has three parts. One is application, and one is the API code, and one is client. Okay, let's discuss about the application first. Um, in The application may have the GUI, graphical user interface, and we may have a requirement to add a programmatic interface to it, or maybe the application was designed under the assumption that it would be accessed only by the API we are designing. Like other application, the application for which API is to be created contains state. That state is dynamic and will change due to the various operations that are executed on it. This state and the operations on it need to be modified and exposed and will form the API we are designing. Now let's discuss about the API code. The API code, this API code accesses the information, uh, accesses the uh, okay, this API accesses this application, um, the application state, as well as the uh, operations on that stage by the application. It uses the application interface, and then it access the application state. And after doing that, it expose it as the RESTful API. In between the application interface and RESTful API, there is a transformation step that adapts the application data model and makes it comply with the RESTful architecture style. And now, after discussing about API, let's move to the client. The client consumes the RESTful API. Okay, the RESTful API created from here is consumed by the client um, uh, using the standard HTTP protocol. Client uses the HTTP library to access the RESTful API. We are we are even able to use the generic REST library on the top of the HTTP library. Okay, now let's discuss about the REST resource data representation format. Before resources are communicated to the client over an HTTP connection, they need to be serialized to the textual representation. This representation can then be involved as an entity in an HTTP message body, and those they may have different formats like one is a JSON format, another can be YAML format, another can be XML format, another can be HTML format.
Can I interrupt you? How can you represent data in HTML format?
Okay, I haven't shared it over here, but I have seen while I was doing the research. Uh, I can't exactly tell you over here, but I have heard it. We can do that.
The other three looks pretty
Yeah,
standard,
we can.
but HTML format.
Yeah, I was also surprised, but I saw that you could
You can,
do this also.
yeah, you can do it. Let's suppose it's a news content, so you can get the data back in the HTML format, which you can plug it in your website directly without any transformation. So data coming back could be in HTML too.
Yeah, I think it was like that only.
Yeah.
I was also just surprised.
Okay, go ahead.
Okay. Okay, and I'm just going to try to discuss about the REST characteristics. Um, uh, One is client characteristics, client server's characteristics, and the client server's characteristics is a pool-based interaction. It has a in REST it is a pool-based interaction style. Client requests data from servers as and when needed, and it is stateless. Each request from client to server must contain all the information necessary to understand the request and cannot take advantage of any stored content on the server. And another is cache. To improve network efficiency, responses must be capable of being labeled as cacheable or non-cacheable. And another is uniform interface. All resources are accessed with a generic interface, that is HTTP GET, POST, PUT, delete. And another is named resources. The system is comprised of resources which are named using a URL. Interconnected resource representation. The representation of the resources are representation of the sources are interconnected using URL, thereby enabling the client to progress from one state to another. Okay, now after that, I ha I have not studied a lot about this REST with JSON, but I have seen some things about it, and then uh, it has a lot of advantages, and among those lot of advantages, I have included some of them. Okay, the first one is standardization. Uh, REST plus JSON forces a discoverable data-oriented API design format that is standardized across the company. This helps the business to to go to pivot the new use cases and uh, extra value from the existing data set. Okay, and another is it makes things easier. It, it makes everything easier to reason about the system responsibilities across a 2 or 3 tier architecture. And then it also reduces the cost. It can use a framework like YQL or GraphQL to transfers, join and transfers the data graph in arbitrary ways. This greatly reduces the cost. And uh, easier to build the tooling. Um, and using REST plus JSON, it is easier to build the tooling. For example, uh, we can monitor the framework that grabs out uh, latency by endpoint and HTTP verb. And another is it has a wide language support. Uh, means there are so many languages it can support. And then uh, one one very important advantage is it is highly debuggable because um, it is human readable. It can be easily read by human, and then that easily human readable format makes it easier to prototype. And okay, so there are so many choices right now. You can even use cloud services, Azure, Amazon web services, and all. Um, I am just studying about this in my distributed web applications classes too. We can see over there too. We have and they are a lot easier than this, but I still wanted to approach with not cloud services, and then uh, lean towards other technologies. And it is not that you are not going to use RMI or RPC right now. They are really good for the people who start distributed computing. um, they are You can take the initiations from RMI, RPC, and it is your call which one to use. There are a lot of them right now, and these are my references. That's it. Thank you.
You mentioned that GMS is a modern system, modern replacement for RMI, but is it like the latest edition is like 5 years old or something?
Yeah.
How fresh is your research?
See, I have I have searched for so many things, and then I found this one for us to do. There was EJB too, but while searching, I didn't find a lot of components. Means a lot of things about that. That is why I didn't do that.
Because somewhere on your slide you mentioned that this is Sun Microsystem that supports GMS. Sun Microsystem gave up with Java 4 years ago, and probably GMS is no longer a good candidate to be called a modern replacement of RMI.
Yeah, but I was about to include EJB along with Java because EJB also uses some, so we can use RMI or RPC in EJB too. And then I was trying to discuss about it, but I didn't find a lot of resources on it, and then I decided to link towards it.
All right, thank you.
Thank you.
We have the next candidate.
Yeah, I can go next, Dr. Baev, if that's okay with Ramonica.
Move on.
Can you hear me?
Yes, I can.
All right, good evening, guys. My name is Brad Shiver, and for my research topic, I decided to look into the scalability of SQL Server, specifically Microsoft SQL Server. When we talk about database management and performance in regards to distributed systems, we need to consider how our system behaves and can adapt to handle and changing loads, or number of transactions or number of connections. So today I'd like to just talk about how SQL Server scales, some of the different approaches in different environments that we could deploy a scalable database, and also have a case study that illustrates the benefits that this particular company found from scaling with SQL Server.
By SQL Server, you mean Microsoft solution? Brad? By saying SQL Server, you mean Microsoft solution? I can't hear you.
Yeah.
Can anybody hear him?
No. I think.
Can you hear me now? I'm sorry.
There was an echo before too. I think there is some sort of problem.
Can you hear me now?
Yes.
Yeah.
By
Okay.
SQL Server, you mean Microsoft solution?
I am referring to Microsoft SQL Server.
Okay.
I'll reference relational databases in general and scaling terms in general, but I concentrated on Microsoft SQL Server as my example. So when we refer to scalability, we refer to the capability of the system to handle a growing amount of work, or its potential to perform more total work in the same elapsed time when processing power is expanded to accommodate growth. System said to be scalable if it can increase its workload and throughput when additional resources are added. There we go. When we talk about scaling, the types of scaling, typically relational databases and Microsoft SQL in general can scale vertically or horizontally. I found some conflicting, nothing official, but just user opinions on some message boards about the horizontal scaling capability, but I'll mention that in a little bit. So when we say vertical scaling, we're also referring to scaling up or scaling down. This is simply adding resources to existing servers or existing instances. There's some benefits associated with vertical scaling. It tends to be easier to integrate with existing code. What I mean is, if you were to scale up a database server, there wouldn't be a lot of rework or any virtually any rework needed from the development side for that code to access the instance, the database. It results in a less complex environment, which is easier to administer, easier to maintain. And there can be some cost savings as far as data center space, power, and cooling. Some of the drawbacks, licensing costs have to be considered, especially if you look at Microsoft SQL Server's per core licensing. Whenever you would add hardware, add CPUs, you would have to account for those and possibly purchase more licensing. The hardware required to run these high-end systems can be quite expensive. And even still, even with the high-end hardware, they do have limitations, even though they may be vast. There are still limitations. When we talk about horizontal scaling, we're referring to scaling out or scaling in. This essentially is adding nodes or instances. The benefits of horizontal scaling, your hardware costs can be cheaper. And what I mean by that is you don't necessarily need the high-end servers when you have many, what they call commodity servers, cheaper servers, or I shouldn't say cheaper, less expensive servers in a cluster. That can reduce some hardware costs on a per server basis. Also, adding and removing nodes can be relatively easy. Distribution of data affords some resiliency and fault tolerance. There are some drawbacks. It's a much more complex environment. It kind of gets tricky when you try to spread the load across or partition the load across different servers or instances. There's probably going to be some code changes that take place or some middleware intelligence that routes the data, some data dependent routing, and also again licensing from a different perspective. You do have to consider licensing of multiple nodes. Each would have to be licensed individually. And then there's some network complexity just to eliminate any inconsistencies in data, especially if the data is distributed across larger distances. So this is the illustration I found that kind of sums up in one image exactly the difference between the two types of scaling that we typically see in relational databases and Microsoft SQL Server. Obviously, the bulky large image or depiction is the vertical scaling, where you simply add resources or bulk up, and the horizontal scaling would be where you add more instances, more numbers to the solution. So I found when I was researching this specific to SQL Server that vertical scaling has been traditionally favored, mainly for the benefits I mentioned on the previous slide. Horizontal scaling is possible. I found some conflicting opinions on this. Some people even went as far as to say it wasn't possible or it wasn't true horizontal scaling, but Microsoft provides a way to scale horizontally, typically either where all nodes can handle read queries and one node writes, or it can be partitioned into shards in which each node can read or write based on the data it's responsible for managing. Also, the SQL Server, the nodes, the partition has to be managed, and that adds that complexity in your development piece, because like I said, either the application has to have some kind of intelligent way to route that data to the correct node or subset of nodes that is responsible for that data, the data dependent routing. Another caveat is the ability to deploy your databases in cloud environments. We call them host environments. Azure offers a really nice platform for deploying and managing your SQL Server. Some of the benefits include more efficient utilization of resources, lower eliminated hardware costs, flexibility, automation, hybrid environment is available if you need that. Physical administration of hardware is reduced or eliminated in terms of the database if it's completely hosted. And then those data center costs, the power, space, cooling, etc., are reduced as well. As Azure offers a lot of tools which provide flexibility. Their elasticity suite helps with splitting up of the partitioning of the data into shards, or not the actual splitting, but the management of that piece. Also, you benefit from being in a high availability environment. You can do your geographical separation of data if needed. And we'll see how DB01, the case study, benefited from the Azure deployment. So DB01 is a financial tech company. Their primary platform is a reporting software that is used across the financial industry. In lending markets, they saw a significant amount of growth after the 2008 real estate crash. As a result, the demand for their product, their solution, the reporting grew exponentially. They found that they were suffering from performance issues in which it would take sometimes up to 30 seconds to complete certain queries. They brought in some specialists. Their database was currently designed on a Postgres environment. Well, it's kind of a hybrid environment between Postgres and Amazon. As we can see, the excessive query times was a real sign that they needed to make a change. They did implement some workarounds. Some of the challenges they had was everybody internally, it was a strong Linux-based foundation, Linux-based environment, and they wanted to keep that if at all possible. Some of the workarounds they did, as I said, the database was split, where the smaller data sets was in Postgres, and the larger data sets were in Redshift. In the Amazon environment, queries on the larger data sets were too slow for Postgres SQL, but the latency in Redshift was too high. And again, they hired a Postgres consultant to try to optimize some of their queries, and his feedback to them was this is not a practical use case for not only Postgres, but for any SQL database. What they ended up doing was they narrowed their list of, they started looking for a new solution. They narrowed their list down to the ones mentioned there: Elasticsearch, Druid, Spark, and SQL Server. SQL performed better and provided the scalability they desired. For their environment, they were allowed to parallelize queries across 16 or 34 cores, which made a huge difference in performance. Higher compression rate, also reduced storage by up to 3 times. And also with the latest version of SQL, they were allowed to move, they were allowed to get the Linux support. SQL is able to run on Linux now. So, and they also decided to move their entire environment to Azure to take advantage of that functionality. So their database environment consisted of 100 cores running 4 instances of SQL Server. The setup runs 40 databases ranging in size from 50 to 500 gigabytes. The benchmark testing showed that SQL Server 2017 on their Linux preferred environment greatly improved their performance and gave them the solution they needed. And those are my references. And does anybody have any questions?
It's not a question, it's more a comment. It sounds strange that Microsoft been very different from Linux nowadays to integrate to Linux environment.
I found that strange as well. I had read that before doing this research, and typically I found that Microsoft wants to urge everybody to use their products or PC-based products. I found it very odd that they did decide to go to supporting a Linux-based platform, and I don't know what their official validation for that is.
Okay, we probably just need to wait for new solutions to raise. Any other questions? All right, thank you, Brad. We have the last presenter, I believe. Monica, you here?
Can you hear me?
Yes, I can.
Okay.
Can you try sharing your screen?
Yes. Can you see my screen?
Yes, we can.
Okay. Good afternoon. I'm Ramonica Scott, and my presentation is on cloud computing. I'm going to start off just giving an overview of cloud computing, and then I'm going to go into the technical details. Cloud computing allows remote access to resources that can be shared amongst clients. Communication with cloud computing is typically done by accessing a front-end interface that connects to a back-end interface through a network such as a virtual network or the internet. The front end is the visible part that allows a client to invoke the cloud. There are a variety of interfaces that can serve the purpose of the front end. A web page initiated from a desktop computer or a mobile device such as a smartphone or tablet can be used to access the front end of the cloud. The back end is where all the shared resources are located. Resources in the back end could consist of items such as data storage systems, virtual machines, software, and hardware. These resources can be local or dispersed in different regions. Definition of cloud computing according to the National Institute of Standards and Technology. The National Institute of Standards and Technology is a measurement standards laboratory agency with the United States Department of Commerce, and its mission is to promote innovation and industrial competitiveness. Their definition is cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, such as network, server, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. They list 5 essential characteristics of cloud computing, which is on-demand self-service, which allows clients the ability to access cloud resources at any given time without service provider involvement. Broad network access allows a variety of client platforms to access the cloud via a network. Resource pooling allows the provider to share resources amongst clients. Rapid elasticity allows the client to quickly add or remove resources when necessary, so they can scale out or scale back at any time. And measured service allows the client's resource usage to be monitored so that proper billing is provided and so that resources can be optimized. There are 3 service models: software as a service, This type of service gives clients remote access to software that is hosted on the cloud. Platform as a service. This type of service gives clients the ability to deploy and run their own created applications on the cloud. And infrastructure as a service. This type of service gives clients the ability to control the operating system, data storage, their own deployed applications, and some networking features. They can create their own virtual machines on the cloud service, on the provider's cloud. And last, included in the definition are the 4 deployment models: a private cloud, which is the cloud infrastructure that is dedicated to one organization; community cloud, cloud infrastructure that is dedicated to a collective group of organizations that share common interests; public cloud, infrastructure that is open to the public; and hybrid cloud. It combines 2 cloud infrastructures, such as a public or a community or private, so that resources can be shared. Technology. I've listed a couple of technologies that are behind cloud computing. And the first is distributed computing. The infrastructure of cloud computing uses distributed computing to connect clients with resources such as applications or data. The resources can reside on different virtual machines, or the resources can reside on servers in different locations. With distributed technology, resources are more likely to be available when there is a failure. If there is a failure with a resource in one location, the workload can be distributed to another location where the data is accessible. Another benefit of cloud use and distribution is that distributing resources speeds communication for global services by enabling more responsive communication. The second technology is virtualization. Virtualization is an important factor of cloud computing. It plays a big role in making sure that cloud computing provides resource sharing and scalability, which are 2 essential characteristics provided by the NIST, the National Institute of Standards and Technology. It provides efficient resource utilization, and cloud computing by allowing multiple applications and operating systems to run on the same server. With virtualization, the client has no idea that they are accessing a virtual machine instead of a host machine. Virtualization refers to the creation of a virtual resource, such as a server, desktop, operating system, file, storage, or network. Virtualization maximizes resources by reducing the number of physical systems, by introducing more virtual systems, thereby making computing more scalable by consolidating multiple workloads. Virtualization technology is made possible due to hypervisors and virtual machines. A virtual machine is an operating system or application environment that is installed on a computer. The virtual machine software runs in a window like other computer software. It can be considered a computer within a computer. The virtual machine is a sandbox from the rest of the system. Any software installed inside the virtual machine can't harm the host computer. And multiple virtual machines can run simultaneously on the same physical computer. Each virtual machine provides its own virtual hardware, including CPUs, memory, hard drives, network interfaces, and other devices. The virtual hardware is then mapped to the real hardware on the physical machine. Even though virtual machines run on the same physical machine, virtual machines are also logically isolated from each other. Virtual machine has no knowledge or dependence of any other virtual machine on the host machine. This isolation contains crashes, errors, or malware attacks solely to the virtual machine that is affected. Also, using virtual machines instead of using a physical computer eliminates the amount of hardware that is needed, since virtual machines shares the hardware of one host machine. This is one reason why cloud computing is an affordable choice. Virtual machines can easily be moved, copied, and reassigned between host servers to optimize hardware resource utilization. Virtual environments are easy to simplify backups, disaster recovery, new deployments, and basic system administration tasks. The virtual machines can be cloned or templated, which makes it very easy to replicate. And my next screen is a screen showing the difference between a traditional on-premises data center and a virtualized computer infrastructure. And as you can see, the virtualized computer architecture is utilizing more resources by creating different operating systems that can host multiple different applications. Or it could host different servers, database servers, and the traditional computer architecture is limited by the one operating system. Scalability in the cloud. Virtualization makes it easy to scale out or scale up in cloud computing. Scaling out, which you can increase the size of a certain virtual machine, or you can scale up by adding more virtual machines. When an application demands more from a virtual machine, you can either give the virtual machine more resources so it can handle demand by itself, which you're scaling up, or you can spin up more virtual machines and disperse demand among them, which you're scaling out.
Should be the other way around. Like scale up, it's actually increasing the property of a VM, but scale out is to make more nodes.
Yes, scaling up, you will add more virtual machines, and scaling out. Did I say that backwards? And
I think your slide is. I think your slide shows it wrong, because scaling out, at least in my understanding, is when you increase number of nodes. But scale up, this is similar to vertical versus horizontal scaling that Brett was talking about. So scale up is determined from the vertical scaling when you increase the property of a single machine, but scaling out is should be associated with horizontal scaling when you increase number of nodes. In your slide, you have titles and the description kind of crossed. I could be wrong. Maybe you use some source that has some justification to this notation, but
okay.
Yes, go ahead. Sorry for interrupting.
Thank you. The next technology that I will discuss is storage. Storage virtualization creates an artificial view of the storage, which hides the physical infrastructure from clients and servers by using a process to group the physical storage from multiple network storage devices so that it looks like a single storage device. With storage virtualization, remote storage devices are made to look like they were directly attached to the system. An advantage of storage virtualization is that it provides better optimization of performance and speed. Also, storage virtualization makes it possible for applications to access needed storage without having to know where it's located or what type of storage device is being used. It makes it possible for stored objects to be moved from place to place or from one type of storage device to another. It makes it easy for multiple clients or tenants to share the same physical storage device without knowing that other clients are using the same device. With storage virtualization, applications and data can be spread over a number of storage devices and storage servers to improve overall storage performance. This functionality can be used to improve storage reliability. Data can be duplicated by storing the data in the same data in several storage devices or storage servers. If one storage device or server fails, the data can be reconstructed because it's duplicated on different storage devices. And my last technology behind cloud computing that I would like to discuss is virtual network. Without a virtual network, the network just sees that it's connected to a physical computer or server. It doesn't have the ability to see the virtual machines that are on the computer or server. Networks are also virtualized with hypervisors, allowing networks and network devices to be created, changed, managed, and destroyed entirely through software without ever touching physical network devices. In network virtualization, multiple subnetworks can be created on the same physical network, which may or may not be authorized to communicate with each other. This enables restrictions of file movement across networks and enhances security, and allows better monitoring and identification of data usage, which lets the network administrators scale up the networks appropriately. It also increases reliability as a disruption in network doesn't affect other networks. And that's the end of my presentation. Thank you.
Thank you. Do you have any questions? All right, thank you everybody for joining this presentation event today. I would like to remind you that I still need some kind of submission on D2L because this is the only way for me to provide the grade for your presentations. So that's not submit. You could submit PowerPoint files or anything. Just submit. And another announcement that
sorry, Dr. Wave, your can understand you actually. I'm gonna be mine.
Can we? Is better? Is better? Is better now?
Yes.
It's echoing right now.
Another announcement: the final test, the take-home final test, will be available from midnight today or tomorrow. So it's 12 a.m. coming midnight, and it will last till 10 p.m. on May the 2nd. It's pretty much a discussion over some topics in distributed computing. It's not something that you want or can find in books. I'm more interested in hearing your opinion on those topics. So feel free to express your opinion. Don't limit yourself with only academic statements or definitions. It's more or less a free discussion on topic.
Okay.
Any questions?
I have no questions.
Good. All right, so we dismiss for today. This presentation event was recorded. If for some reason